Welcome back to Hacker. In this video, we're going to tackle an essential problem for code interviews, Decode Ways from LeetCode. This problem is great for mastering dynamic programming and understanding how to handle recursive patterns in string manipulation. We will explore three approaches: Recursive Solution, Dynamic Programming top-down, and bottom-up approaches. Let's break down the problem step by step and understand how these solutions work. So sit back, relax, and let's dive in. So what is the problem statement? You have intercepted a secret message encoded as a string of numbers. The message is decoded by a following mapping. 1 is mapped to A, 2 is mapped to B, and so on. 25 maps to Y, and 26 mapped to G. So basically, here is a conversion table. So each letter in the alphabets maps to numbers from 1 to 26. Okay. So however, while decoding the message, you realize that there are many different ways you can decode the message, because some codes are contained in other codes. That is, it is a double digit code. Like when you consider 11, so this 11 can be decoded as what? It can be decoded as K or 2A's, right? So that's how. Similarly here, 2 and 5 and 25. So when you take 25, it is a Y. So but 2 is a B, 5 alone is a E. So basically here you can't figure out how to decode it. So this is the tricky part of the question, okay? For example, 11106 can be decoded into what? JF. Basically, we group it as A, which is 1, and another A, which is 1, and J, which is 10, and F, which is 6, okay? And next way is K, which is 11, as we discussed here, and J is what? 10, and F is what? 6. And another grouping is invalid, we see here. Why? So 1, 11, and 06. This is invalid because 06 is not a valid code. Only 6 alone is a valid, okay? But 06 is definitely not a valid code. In that cases, we have to discard that path, okay? So the path which we decoded it, that is not a valid path. So that's why we have to discard that path, okay? Note, there may be strings that are impossible to decode. So they're saying that not all strings are possible to decode, okay? So we are relieved, because like, what if some string contains 0 in between like this while decoding? Then we can just say that we can't decode. Given a string as containing only digits, return the number of ways to decode it. If the entire string cannot be decoded in any valid way, return 0. Okay, so basically we have to return the number of ways to decode the given string. So if string can be decoded, we can return 0. Okay, the test cases are generated so that the answer fits in a 32-bit integers. So basically we don't need to worry about the integer overflow as well. So let's look at examples. So in example 1, we have s is equals to 1, 2. So basically we can decode in two ways. We can take either as a comma b, which is what? 1 and 2, and we can take this 12 as a character L. So basically L maps to 12, right? So that's why we can decode it in two ways. One is A, B, and next is taking L alone, okay? So there are two ways of decoding it. That's why we written 2. So example 2, we have s is equals to 2 to 6. So here, how can we split this? Okay, basically 2 to 6. Right, so here we can split into like 2 and 26. This is one split, and we can split as 2, 2, and 6, and we can split as 22 and 6. So here this maps to what? This maps to B here, and 26 is maps to G. So this is one BG, and next is what? 2 to 6, which is what? B, B, and F. Okay. And next is 22 and 6. 22 maps to what? Our V, and 6 maps to our F. So basically we can decode as three ways. So that's why we have written 3 here. Example 3. So here this is one of the classic cases where we can't decode the given string. Basically when we have a leading zeros, that means that a 0 appears before the first non-zero digit. So here 0 appears before 6. So this can't be translated to any of the letters we have, right? So the valid thing with zeros are 10, 20. And here when we get any the things like 01 to 09, we can't decode it to anything. So that's why we return 0, because this is an invalid case for us. This leading 0 is what makes it impossible to decode, okay? So let's look at the constants. What is the first constraint? They mentioned that S length is in the inclusive range of 1 to 100. So what should we get from this? So basic thing is we can perform only 10 power 8 operations per second. Okay, so apart from that, it would be time limit exceeded. So if we consider n is equals to 100, so which is the upper limit of the string's length, so we can perform only till n power 4 operations. So what is n power 4 here? 10 square whole power 4, which is 10 power 8. So our solution would be accepted till n power 4 operations per second. Okay, so this is what the maximum time complexity our solution should have. Next is they given us S contains only digits and may contain leading zeros. So when it contains only digits, it's just like we can decode the string, and when it contains leading zeros, we can just straight away return 0, because we can't decode it into any string possible. Okay, so that's why we have written 0. So these are the two constants given here. So this is the boilerplate code given, wherein we have a num decodings method which takes the string s and returns the integer. So this integer is what? This is just the number of ways to decode the given string. Okay, let's look into the solutions. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. Firstly, let's explore the recursive solution. So what is the intuition here? The problem involves decoding a string into valid letter mappings. That is, a is equals to 1, b is equals to 2, and so on, g is equals to 26. Using recursion, we explore all possible decodings by making decisions for single and double digits at each step. So basically, here we see in the example 2, right? So we can consider either a single digit or double digit at each step. So, but considering double digit, we can do only when the given two digits are in the inclusion range of 10 to 26, because our double digit range starts from what 10 and it ends at 26, and we don't need to care about three digits because we have the letters only from 1 to 26. Okay, so after this we don't have any mapping, so that's why we consider for the single digit each time, and for double digit we have to consider only if these two consecutive digits are in the inclusion range of 10 to 26. Okay, so in that case only we have the possibility to consider for the double digit. Okay, the goal is to count the total valid decoding paths. So basically here at each step, as we find the ways, we just do addition because we have to return the total valid decoding paths, right? So that's why the moment we find the valid decoding path, we just add it to the total ways. So that's the idea, guys. Let's go into the algorithm. In step 1, define a helper function to recursively compute the number of ways to decode the string starting from the specific index. So basically here we're defining a helper function to decode the string, and this helper function takes the specific index to decode the string. Okay, so here in step 2, if the index equals to string length, return 1 as it indicates a valid decoding path. So how does it indicate a valid decoding path? If index is equals to string length, that means that we exhausted all possible indexes we have from the string, right? So basically the valid indexes are from what I is equals to 0, and the maximum valid index is what length of the string minus 1. So what if the index is equals to length of string? That means that we exhausted this valid index as well, and we are able to reach the end of the string, and that means that till that point we are able to decode it. So that's why it's a valid decoding path, and we return 1. And next thing, if the character is 0, we return 0 because this is what the leading 0 case, right? Here we just discussed in the example 3. So in that case, we can't decode this further. That's why we just return 0 because 0 ways to decode it. So, and in step 4, we explore the two possibilities: decode one character and decode two characters. This only if valid. The valid condition is we just discussed, right? So the characters which we are considering should be the inclusion range of 10 to 26. In that case only we can consider for the two characters. Okay, so and we don't need to care about three characters because we only have the letters from 1 to 26. Okay, so that's clear, right? In step 5, we return the sum of the decoding paths from both options. So basically here we just need to sum up the all possible ways, right? So that's why we have to do the sum here. So here they ask for all possible ways. So that's the key point which would help us to make a decision that we have to do sum. So let's look into the code now. So firstly, we define our helper function, which is recursive in nature. This takes the index parameter. So here we define our base cases because for any recursive function, the base cases are mandatory. Without that, the recursive function would keep on calling itself and it would lead to recursion depth exceed error. So to avoid hitting that case, we have to define the base cases which would help the function to stop at some point of time. So what are the base cases here? So when index is equal to the length of the string, that means that we traverse to all possible valid index of the string. In that case, we were able to decode the string. So we have to return once. It indicates the one way of decoding the string. Okay. So that's why we return 1. So another base case, this is for the invalid decoding cases. So when s of index is equal to 0, that means that current character in the string is 0. So this is the case where we have a leading 0 as we have in example 3. In that case, we can't decode the string, right? So for that case, we have to return 0. Step 4, decode single and double characters. So firstly, we decode the single character. So for decode the single character, what we do, we just call the helper of index plus 1. This means that we consider this index in current recursion, and for the next recursion, we are passing index plus 1. That just represents we consider only one index for the current recursion. So this is the way of decoding single character, okay? And we store the total number of ways in total, okay? And next is decode the double character. So this we can't just simply do like that, right? So firstly we have to check the range of the index also, right? If index is beyond the length of the string, then we can't consider the double character, right? So that's why firstly we have to check if index plus 1 is less than the string, then only we can consider the double character, because we have to consider the current index and index plus 1 for the double character, right? So that's why we have to have this check, else it would be out of the bounds. That's why we just have this check. And next check is the what is the double character is making up to here. So if the double character is in the range of 10 to 26, we can make it. So here we are just slicing the string and converting the integer. So basically, so index is what? The current index, and index plus 2. This would give us what? This is the exclusion range, right? So that's why it would get the string only till index plus 1. So it means that we're just getting only 2 characters consecutively. So we are checking if these 2 characters are in the range of 10 to 26. In that case only, we can consider for the double character, okay? So these are 2 checks we have. So you understood, right? This index plus 1 check to ensure that we are not going out of the bounds. And this check ensures that we are considering only the valid characters, that is from the 10 to 26, okay? So similarly, for getting the double character, we just pass helper of index plus 2. This is to say that we consider the index and index plus 1 for this current recursion, and for the next recursion, we pass in index plus 2. That's how we get the ways for decoding the double character. And observe here, we are adding this result to the total. It is not that we just storing data to total, because firstly, we have this single character ways, right? And next, we add the double character decoding ways. So that's the idea, guys. Basically, we want the total number of ways, right? So that's why we have to sum it up. And at the end, we just return the total decoding ways, which is total, okay? So this is our helper function. Here in the num decodings, we just return the helper of 0, which is to say that we start our index from 0 and keep on exploring the possibilities of single character decoding and double character decoding. Simple, right? So what are complexes here? The time complex is O of 2 power n. At each index, we explore the 2 paths, single or double decoding. So basically for each index, we have the 2 choices, either to consider single character or double character. So likewise, how many indexes we have? N indexes. So totally what? This is like 2 into 2 into like what? Till n. So this is what? 2 power n possibilities. That's why it's O of 2 power n. And the space complex is O of n due to the recursion stack. So basically the maximum length of the recursion stack would be n. After that, it keeps on processing and returns the result. So that's why it's just O of n. So I got the code ready here. Let me try running this. So this asks solution for the 3 cases. Let me try summon this. We see that time limit is exceeded and only 23 out of 269 test cases are passed. This is because we have an exponential time complexity and it won't be scalable for the larger inputs. So that's why we have to optimize the solution. So let's look into the optimizations. So let's look into recursion stack, which would help us to identify the bottlenecks in the current approach. So I'm considering the example 2, wherein we have s equals to 2 to 6. Okay. So here we just start with 0th index, right? And after that, for each index, we explore the possibility of considering 1 index and 2 indexes. So that's why we make call with plus 1 and plus 2. And similarly here as well, plus 1, plus 2, plus 1, plus 2, so on. And we stop making calls once we hit the base cases. Okay. So that's the idea. So here, once we reach the 3, it is no longer a valid index. That's why we stop here. And here, once we reach the 4, it is also not a valid index. We stop here. Similarly for all these things. Okay. So now let's take a closer look. So what exactly is happening here? If you see here, helper of 2 is called for twice. Helper of 3 is called for thrice, and helper of 4 is called for 4 times, and helper of 5 is called for twice. So basically, what should we understand? Here, the same problem is computed again and again, even though the result of the same problem would be same every time, right? So here, the result of this problem won't be changing even if we compute it for 100 times. So why not storing these results once and use it for the next time we encounter this? That would be optimizing our solution, right? So that's the idea, guys. I'm talking about top-down dynamic programming approach. So you got the idea, right? So basically, once we compute the result of the subproblem, we can store it and use for solving the bigger subproblem. That's the key, okay? So let's look into approach 2, which is top-down dynamic programming approach. This is based on the memoization concept. So what is intuition here? The recursive approach has overlapping subproblems. By storing results of previously computed states, we can avoid redundant computations, reducing the time complexity significantly. So basically, if you see in the recursion stack, we have a redundant computations here, right? So once we compute the results for helper of 2, we don't need to compute it again. That means we can just store it in some storage. Then next time we can just use it from the stored result. So this way we would save our computation time, which would help us decrease the time complexity of solution, right? So that's how it will help in optimization. So let's look at algorithm. Step 1, use a dictionary to memorize results for each starting index. So basically here in the recursion stack we see, right, the only thing changes is what, this index. If we consider index as a key, then that would be suffice, right? So that's why we would consider this index as a key to our dictionary. Okay. Step 2, implement this same logic as a recursive approach, but first check if the result for the current index exists in the memo. So basically the logic is same as our previous recursive approach, but here we just have another check. So we just check if the result for the current index exists in the memo. Okay. In step 3, if S, return the memoized result. Otherwise, calculate the result recursively. So basically, if the result exists, we just return the memoized result instead of computing again. So if the result doesn't exist, we have to compute the result using recursion. Okay. In step 4, we store the result in the memo and return it. So basically, before returning it, we store the result in memo. That's the idea, guys. So it's almost same as previous approach. We just use of a memory. Okay, that's all. So here the logic is almost same as previous approach, but just that we have some few line changes. But later point of video, I'll tell you with just one line of change, how can we convert this into a memoized version. Okay. But now let's look into this code. Okay. So firstly here we defined our dictionary, which is memo here. Okay. So here, and we have the same recursive function. So we have same base case as previous approach. So what is changing now? So here this step 4 is additional here, right? So here we checking if the index exists in memo. That means we checking if the result is already computed for this particular index. So if that is the case, we would have stored in memo. So that's why we check if index in memo, we return memo of index. That means we return the result of that particular index. Okay. So this is the additional check we have, and this is similar to previous approach, the decode single and double characters. So here this is the same, and see here we were returning total, but here what we doing, we are storing total in memo of index, then we return total. That means that before returning the result, we store in our memo. That's how when we encounter the subproblem again, we don't need to compute it again. We just can look in memory and return it, as we see here. Okay. This is our helper function definition. So here we just written helper of 0 as previous approach. So what are complexes here? The time complex is O of n. For each index, we compute only one side. So it is O of n. Basically, we have n states and we compute only once. So that's why it's O of n. And the space complex is O of n. This is for the memoization and recursion stack. So basically, for memoization, we want the storage, right? So if we have the string of length n, we want n states to be stored in our memory. So that's why it's n, plus our recursion stack also takes space n. So that's why it is O of 2n. But this 2 is actually negligible in front of n, so it is O of n. Okay. So now I'll be showing you how to convert this recursive version into memoized version with just one line of change. We just need to add trait of cache annotation, guys. So let me just summarize this. So we see that this accepts solution. So basically, how does this get accepted with just one line of change? So here, add trait of cache annotation would be acting similar to our hash map. So basically, what is happening here is, if the call comes to the helper function for a particular index, it first computes it. Next time, if the call comes to the helper function of the same index, then it would be looking in the cache and returning it. So basically, it would compute once and then reuse the results for the next time. That's how our add trait of cache annotation would help us convert this recursive function into the memoized version with just one line of change only. Okay. So now I got the code ready for a top-down dynamic programming approach using the hash map. Let me try running this. So this accepts solution for the 3 cases. Let me try submitting this. So we see that this accepts solution. Cool, right? So let's look into the approach 3, which is bottom-up dynamic programming approach. So what is the intuition here? Instead of recursion, use a DP array to iteratively compute the number of decoding ways for each substring. This eliminates the recursion stack and reduces the space complexity. So here the time complexity remains same, but the space complexity would be reduced because we won't be using the recursion, and this reduces the space required for the recursion stack. Okay. So let's look at the algorithm. In step 1, create a DP array where DP of I represents the number of decoding ways for the substring. So the substring is ranging from what? 0 to I. So 0 to I means what? This is exclusive. So the inclusive range would be 0 to I minus 1. Okay, so this is a slicing, right? This would be exclusive range. So the substring we would be counting is from what? 0 to I minus 1. Okay. So each DP of I represents the number of ways to decode for the substring 0 to I minus 1. This is the indices we have. Okay. Step 2, initialize DP of 0 is equals to 1. So this is for the case of empty string. We have only one way, right, for empty strings. So that's why we initialize it with 1. And handle the DP of 1 based on the first character. So basically DP of 1, we have only one choice, right, to pick the single character. Okay, so we can pick the single character and we can decode it only if it is not equals to 0, right? So that's why we have to have a check based on like if it is 0 or not. Okay, if it is not 0, then we will have a one way to decode it. So that's the idea when I meant based on the first character here. Okay. Step 3, iterate to the string updating DP of I for single and double character decoding. So basically here we have to iterate to the string and then update the DP of I for both single and double character decoding. So we have to check the feasibility for the double character decoding as we checked in the previous approach. In step 4, we have to return the DP of length of S as a final result. Why? Because DP of length of S is what? It actually stores the number of decoding ways for the substring 0 to n. If we consider n is equals to length of S, this means that it would be storing till index what? 0 to n minus 1. Okay, so the string valid index is only till n minus 1, right? So that means that it's storing the total decoding ways for the given string. So that's why we have to return this DP of n or DP of length of S as a final result. Okay. So now let's look into the dry run. So let's consider our example 2 wherein we have S is equals to 2 to 6. So let's have this S is equals to 2 to 6. So let's just form the DP table. So here we have index, we have value. So we'll be having the DP table of length 4. So this 0 is for what? Empty string. So empty string only weighs 1. And for index 1, what we'll be having is we have to process this first index here. So we have 2. That is only one way, right? Because 2 is mapping to B. So it is one way only. So we have to put 1 here. So these two are the base cases. And next are the common scenarios, so the general cases. So next is we have I is equals to 2. For I is equals to 2, we'll be having these two characters in the string. So these two characters can be decoded in two ways. We can take like 2B's or 20T's map to what V. So two ways we have. So that's why the value is 2 here. And next we have 3. So these 3 characters we have, right? That means, so here we have 3 ways. So basically we can take it as 2 to 6, or we can take it as 20 to 6, and we can take it as 226. So these 3 ways we can put it as 3. So now we form this table, but how can we actually fill this table in code? Here we can form this solution from the previous base cases we have, right? So how can we form that? So firstly, we just fill our base cases and rest all would be at 0. Okay. So this is the main key. And then we can get this form from our base case only. So to reach the DP of 2, what should be the possible cases? It can reach from here or it can reach from here. Similarly, for DP of 3, the same cases, like it can reach from here or it can reach from here. So it can reach from the here when it considers for the 2 character length. Okay. So now when we consider the DP of 2, so initially we told that it would be at 0. So let me just put that here. So initially this value is what? 0. So now if it was 0, then it can come from where this and this. It can come from this when we consider the single character. Then we can do +1. And now it can come from here if we do the double character decoding. So it is +1. So basically we can say the recursive relation as what? DP of I is equals to DP of I minus 1 plus I minus 2. This is in the high level, but this always I minus 2 won't be there. This would be there only if it is a valid range for the 2 characters. So the valid range for the 2 characters is what? It should be there from the inclusive range of 10 to 26. In this range only we can consider. This also won't be there when we have the leading 0, right? When we have a leading 0, it won't be mapped to the any of this single digit number here. So that's why this also won't be there in this case. So the main idea is we will be adding this, but based on the conditions we have. Okay, so let's look at the code now. Okay, so firstly here we got the length of the string stored in n. Okay, so if not s or s of 0 is equal to 0, we return 0. Because where s of 0 is equal to 0, it won't be mapped to any of the string we have, right? So basically the first character itself is 0. Then we can't decode this string, right? Basically this 0 won't be mapping to any of the characters from 1 to 9. So that's why we can't decode this and we have to return 0. In step 1, we insert the DP array. So here if you don't get this step, so this is what duplicating this 0 for n plus 1 times. So the syntax is easy. So if you have 0 and you do multiply with 1, so you'll get only 1. If you multiply with 2, you'll be getting the list of 0, 0. So basically this says what value you have to duplicate in the list, and this says what number of times you have to duplicate the value in the list. This is a simple way to initialize the list. Okay, and next we are filling our base cases DP of 0 and DP of 1. This is a tuple unpacking approach. We can even fill like DP of 0 is equal to 1, and next line we can write DP of 1 is equal to 1, but this is a smarter way of doing that. Okay, step 2, update the DP array. So basically we have filled our DP array from 0 to 1. Now we have to fill from 2 to n. So for that we consider the for loop from 2 to n plus 1, because this is exclusive and the indices will be getting only in the range of 2 to n. Okay. And next we have the current index formula, right? That is what DP of I is equals to DP of I minus 1 plus I minus 2. So basically we have correct checks for the I minus 1 and I minus 2. So what are the checks for I minus 1? So we can add I minus 1 only if s of I minus 1 is not equal to 0. So why s of I minus 1 here? So basically what does this db of I store? It stores the total number of decoding ways for the substring from 0 to I minus 1. So in that case, for the current index, what we have to consider I minus 1 from the string. So that's why we're checking I minus 1 character. Okay, if it is not equals to 0, then we can add our db of I minus 1. Because if it is equal to 0, there is no way we can map it from A to I. So that's why we have a check here. And for the double character decoding as well, we have to get the two subsequent characters, right? So that is what from I minus 2 to I minus 1. We have to get these two characters. So for that, we're just slicing here. So I minus 2 to I, because this is exclusive and we'll get only I minus 1 in inclusion. So that's why we first fetching this and then we convert it into integer and we checking if it is in range of 10 to 26. Okay. Then only we can add db of I minus 2 to db of I. Okay. So that's how we fill out dp array. So at the end, we just return the dp of n. We discussed it because dp of n stores the number of ways to decode the substring till 0 to n minus 1. And n minus 1 is the last valid index. That means that it represents the total number of ways for the whole string. That's why we return dp of n. Okay. So what are complexes here? The time complex is O of n because it returns the string only once. And we don't do any recomputation here. So that's why it's O of n. Very straightforward, right? And the space complex is O of n. This is for the dp array we have. So actually here we're forming the dp array of size n plus 1, but 1 is negligible in front of n. That's why it is O of n, okay? So I got the code ready here. Let me run this. So this is the accept solution for the three cases. Let me try submit this. So this accept solution and beats 100% of users. Cool, right? And that's a wrap on solving the decode ways using three different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.